For the next section, we're going to be talking about the different tools that are out there available and the taxonomy of them. Notice that from the last section, we divided data into structured and unstructured data, or abstract data and physical data. This is actually going to be very key to understanding the different tools that are out there. So let's take a look at, again, when we talk about the central visualization engine. When we talk about the visualization engine, we're talking about something that is able to ingest data, then it processes data, so you have some kind of processing algorithm that lets you do something interesting in data. That could be everything from filtering to data mining to creating new data internally. Then figure out a way to actually translate that into something that we can actually possibly display on the screen. So in other words, assign some geometry to it. Notice that physical data already has an inherent geometry to it. The last part is actually how to translate that geometry into pixels, and then how to interact with it, which would be the user interface. So let's look at the first section, processing algorithms. There is two very large toolkits that are very important in data visualization that are mostly about processing algorithms. Both of them were developed in the early 90s, but have grown in strength because they were just very well designed to actually be understandable and be very efficient. The first one is the Visualization Toolkit. The Visualization Toolkit, VTK, mostly applies to structure or physical data. VTK is a series of processing algorithms that can be strung together using C++, TCL/TK, Python, which is now the underlying language for it, as well as Java. Because it's been around for such a long time and it's such a strong package, VTK actually offers you the ability to actually open a window and display the results from your processing algorithms. So it is a little more than just processing algorithms, but at the core, it is a set of processing algorithms. Let me talk a little more about VTK. VTK was actually originally developed as a series of medical algorithms for visualizing data from instruments that were being developed by GE. Eventually, the people that worked for this group spun off their own company that's called Kitware. They created many filters, many algorithms, one of them which became very key to the scientific field, which is called marching cubes, which is the ability to actually create holeless isosurfaces in a volume. This actually held a patent until 2005. Now, the original intent of VTK was to create just an educational tool, to actually create a set of algorithms that they could actually use then to teach visualization. Eventually, it was so well written and it was effective and efficient enough that as computers became faster, the overhead of it being object-oriented actually became a positive. So as they adopted C++ and they used GL and TK for user interface, it became a very strong set of tools. To learn more about VTK, I encourage you to go to vtk.org or kitware.com. So what does VTK have in it? Well, it has basic visualization algorithms that let you deal with scalar data, vector data, tensor data, even textures and volumetric data. As we said before, the basic elements that would define this data are either points in space, triangles in space, triangle strips, and all sort of different kinds of finite elements, and in fact, ways you can even mix and match some of these. Now, you can actually create meshes themselves within VTK. There is implicit modeling. There is tools for polygon reduction, for mesh smoothing. You can actually cut meshes to actually create new meshes that are just a subset of the original mesh. And as I said before, you can have a set of points in 3D space and come up with an envelope or a Delaunay triangulation of these points. There is also a set of imaging algorithms, as well as some basic statistical tools and InfoVis tools within VTK. Now, the opposite side of this for VTK would be InfoVis tool, an InfoVis set of processing algorithms, and the most well-known package nowadays is R. R, just like VTK, was developed in the early 90s, and is actually also meant as a teaching tool for statistical analysis. Eventually, the set of algorithms was so strong that it actually became a full package that many people adopt and use nowadays. It also comes nowadays with a set of visualization tools to actually be able to come up with a screen or create a plot, but at its heart is a statistical analysis tool. So let's skip ahead from processing algorithms. Geometry generation is just basically a mapping from your data into some kind of structure, and let's talk a little about rendering. That is actually the ability of moving these geometric structures into pixels, into something onto your screen. Now we can divide renderers into different categories. The first of all being interactive renderers, things that let you show these geometric structures on your screen at more than 30 frames per second. At the core of this, nowadays, most machines have processors purely made to do this rendering. Those would be your graphics card in your standard laptop or desktop. For that, the language that these graphic cards talk is OpenGL. There is different versions of OpenGL, including OpenGL for mobile devices, as well as a competitor developed by Microsoft called Direct3D. Both are very strong, and they talk directly to the abilities of the graphics card to actually render triangles and points at high frame rates. Many game developers develop directly on OpenGL. There has been many visualization tools that, in order to get the maximum throughput of your triangles, things that you're trying to show, you in fact try to program OpenGL. However, OpenGL is very hard to program. Thus, there's higher level languages like OpenInventor and Java 3D that try to make an easier job of this. Notice that there has been new versions of OpenGL that are done to use your graphics card while being part of a browser, and that's what's called as WebGL. Same as the higher languages that we're talking about before, OpenInventor and Java 3D, there is an API, a package that lets you take a higher approach to GL programming within the web, within JavaScript, called 3JS. So if you wanted to program something that shows something like this, the UTET teapot, your program, if you did it in OpenGL, will look something like the code that we're looking at right now in the background, where you actually have to set up your environment, you have to set up your vertices, and tell the graphics card how to manage these vertices to actually render them as triangles. However, internally, this is exactly the way the graphics card wants to listen to it, and it can actually do efficient things like make lists out of this, so it can render it quite fast. It does this in the GPU, in the graphic processing unit, which actually in of itself can have hundreds of processors inside the GPU. Again, programming OpenGL is not the easiest thing, so there is higher level languages. OpenInventor was a language developed at SGI for this particular reason. That was actually quite easy to use. You could open a window, give it a full 3D model, and just tell it to attach a 3D camera to it, and you would have an interactive, very fast 3D application. In fact, we actually developed some visualization tools here at Caltech for biology visualization based on OpenInventor. In this case, this is a project based on MCell that will let you see the results of some stochastic simulation, where you actually have molecules on either side of a cell membrane, and you would see as the cells went on and off. Notice the GUI interaction at the bottom that actually lets you do this as a VCR kind of control, so you can actually play this animation, as well as select the different molecules that you want or do not want to see. But at the heart is this render window in the middle, which is a fully interactive 60 frames per second or higher window where you can actually spin your 3D mesh and look at it from any point of view and even record a movie out of this. So that's OpenGL, that's OpenInventor, and there's also a version for Java called Java 3D. But another way to look at renderers is not the interactive renderers, but renderers that actually do a much better job of going pixel by pixel and figuring out the color, the shadows, the specularity, emissions of light to actually create a much sharper image. These are called ray tracers. There's a free ray tracer that has been around for a while called POV Ray. And then the industry standard, which used to be very prohibitively expensive, was called RenderMan. RenderMan, as some of you might know, was developed by Pixar and what's used in most movies nowadays to actually do any kind of 3D rendering. What's really interesting is just in March of this year, RenderMan actually became free for non-commercial use, which is quite a big deal. So I'm sure we'll see much more scientific visualization actually being rendered using RenderMan. On the flip side of these ray tracers are what's called modelers. Modelers are graphic interfaces that allow you to interact with meshes, create meshes, tweak meshes, assign different materials to your mesh, and even create full animations out of it. Blender is the open source web standard, while Maya is the commercial version that, again, is very much used in industry. Now, both Blender and Maya actually come with their own ray tracers so that you can see the results from your modeling. However, in most cases, you would export your results to a lighting model, and in industry, you would eventually probably use RenderMan itself. However, there's lots of people in the scientific community that have realized that these tools, like Blender especially, are really good at importing your meshes and being able to already find some interesting information just from tweaking and creating and evaluating your meshes, even with an environment like Blender. So let's look at some results. So let's take a look at some results. These are some renderings from the Blender gallery. They're all biological concepts, but you can tell they're very intricate. You can see the light diffusion. You can see different focus on different aspects. Here are some results from POV Ray. Notice again that in the case of metallic structures, you see full reflections. One of these images can take anywhere from 5 minutes to days to render, each image. Compare that to interactive renders, which can render images over 60 times every second. Here's an image from RenderMan, using, again, the iconic Utah teapot. Now, again, RenderMan is mostly known for its work as part of Pixar. Here's an image from Ratatouille. Notice the detail on the counter, notice the detail on the hair models, and also notice the details or the light emission that's coming from the fire under the pot. Of course, Blender has also been used for scientific visualization. Here are some results from a tsunami simulation from the Arctic Center, Supercomputing Center. I expect that we'll see a lot more results coming out of RenderMan in the world of scientific visualization now that it's open source and free. The last part to this whole thing is the interface, the user interface. There is many GUI toolkits that you can use to actually create your own tools. Qt has become a standard just because it's one of the few graphic user interface toolkits that actually works on many platforms like Linux, Mac, and Windows. There's other GUI toolkits like GTK and TK, which is part of the TK scripting language. And of course, the more modern GUI toolkits that are very popular are the ones for iOS, for app development, as well as Android. Java has its own set of GUI interfaces like Java Swing. And of course, there's platform-dependent also GUI toolkits like Cocoa for the Mac or Motif for most Linux and Unix systems. Of course, you can also develop user interfaces and graphic user interfaces using the web, using a browser. And that's become much more of a default nowadays. You can use dynamic HTML, which is basically HTML5 with access to a canvas area where you can actually render things, as well as create a whole set of interactive buttons and form elements. And you can do this all much easier with the use of JavaScript and a language that actually lets you manage many elements at once, like jQuery and jQuery UI. In theory, for the web, you could also do Java, which lets you do applets. However, restrictions for security on most browsers have made the work of Java much harder for web browsers. Processing is a language that was developed on top of Java to actually make visualization and create visual elements much faster and much easier. For many of the classes that we teach in scientific visualization, to allow students to actually create tools, we have actually adopted processing. Finally, Flash is another environment that lets you create graphics and user interfaces for the web, and is still hanging around for a little bit. But this begs the questions: how do you develop graphic applications for the world of scientific visualization? Well, most modern programming languages have easier ways to actually develop graphics that let you create scientific visualizations a lot faster. For instance, C++ has a wrapper around it called Cinder, which actually lets you create a window quite easily, just within a couple lines of code, and already start throwing visual elements to the screen. This is similar to what processing is to Java. A modern interpreted language called Lua that came out of Brazil actually does the same thing that Python does in terms of memory management, but actually does it quite quickly and lets you do things quite efficiently. Lua had a lot of momentum in the last couple of years. The graphic environments that work on top of Lua are Love and Y. Notice that Objective-C has Swift, and then JavaScript, you could say an easier way to actually create graphics within JavaScript is this language called D3, or this package called D3. We'll talk a little more about D3 in the next section. Finally, there is no really easy way to create graphics in Python. There has been attempts like Kiwi, but they are not mature enough to actually create strong, stable scientific visualizations just yet. Furthermore, one of the big strong points about Kiwi is that it actually lets you create those same applications and export them to a mobile device by translating it into iOS or Android. Now that we talked about user interfaces, now we can talk about things that actually put everything together. We're talking everything from the data creation, data ingestion, processing algorithms, geometric generation, actually rendering it on the screen, and giving you a user interface at the end of it. This is what we call a visualization system. In the world of scientific visualization, we first of all have ParaView. And ParaView is actually a system that was developed at the national labs with the underlying TOOLKIT, which is VTK. Also within the national labs, they have developed Visit, also using VTK. The reason both these packages are quite important is because they have the support of the national labs, which means they don't need a consumer base to be able to subsist and to be able to keep on pushing forward the limits of what they can do and they should be doing. One of the few commercial packages still remaining out there that are available for scientific visualization is Insight. On the other hand, for the world of information visualization, we have a package called Tableau. Tableau is one of the stronger tools out there to visualize information out there right now. Not only does it have the ability to very intuitively display results of different abstract or table of InfoVis, but actually even lets you export it to the web. Tableau has very close connections to the Stanford group, which also developed D3. In fact, many of the tools that they use to actually deploy things on the web are D3-based or very similar to D3. There's other toolkits as well. One of them is Many Eyes, which is kind of a wiki-based tool, as well as other more specific field tools. First of all, let's take a quick look back at scientific visualization tools. Let's take a closer look at ParaView. Here are some results out of ParaView. You can see the inherent 3D structure that we're trying to demonstrate here that comes out of scientific visualizations, scientific simulations. Let's take an example of a classic data set. This is the blunt fin data set from the early 1980s, in which they actually decided to do one of the first fluid simulations to figure out the turbulence that happens as a flow goes over a wing. What they did is they actually created a 3D grid. They realized it would be symmetric, so they only did half of it. And these are the results from the simulation at the bottom. Again, this is one of the first fluid visualization data sets that was actually quite strong and quite relevant and quite interesting to look at. Now, if this is your original visualization that was done in the 1980s, this is kind of the graphic that goes with it. This is what it looks when you open it in ParaView. Through a series of filters, you load the data, you can create clips, you can look at surfaces, you can put vectors to actually signify the direction of the flow. You can put particles that then you actually trace their path. You can do the same thing with streams. You can create slices and color them. So this is a perfect tool for quick inspection of scientific visualization. Of course, you can export the same images in high resolution, and you can actually use them for publications. Here's an example where we use Photoshop to create a much more complex infographic of the same data. Notice on the upper left, we have the original images in these circles from the paper for the blunt fin data set from the 1980s, while in the right, we have the slices of the same data now using ParaView. On the flip side, we have the InfoVis tools. We have Modrian, which is interesting because it actually uses R on its back end, so you can actually do principal component analysis and other statistical algorithms directly from Modrian. There's XMDV, which lots of the different tools that we now use for data visualization have come out of, including hierarchical rings and parallel coordinates. And there's very specific tools to different fields, like there's Molegro for biology, TOPCAT for astrophysics, and we already talked about Many Eyes and Tableau. Here is a screenshot of Modrian. Notice that it's a fully interactive tool, and in this case, we've actually highlighted a set of points, and when we highlight a set of points in one particular plot, it highlights the same information across the different plots. This is a really great example where a full system with an interactive capability lets you discover and analyze your data much quicker and much faster. This is actually the data set from the Fisher's iris, which you probably saw from earlier talks in data mining. Here is a series of screenshots from TOPCAT. Because it is mainly used by the astrophysics community, it has lots of interesting tools to visualize things in polar coordinates or on a sphere. Here is a screenshot of IBM's Many Eyes, which is a wiki-based system. What this allows you is to actually upload your data into this wiki environment. It gets automatically published to the community. And then immediately from there, you can actually start applying different visualization filters to it. Then you can actually republish your results of the specific visualizations and share them with the community as well. It's not only interactive, but actually allows you to share your progress and your discoveries with a group of coworkers. From the same group from IBM actually came the idea of Wordle, which was very popular many years ago, which is a way of actually visualizing text by ordered by significance. Here is a screenshot of Tableau. The key thing to notice about Tableau is that it's actually quite an intuitive environment. Any of the variables that you have available, you can drag them directly onto the plots, and it'll try its best effort to understand what possibly that could mean in terms of creating interaction or in terms of creating complex plots. We also talked about these three: D3 is an environment within JavaScript, within the web, that lets you handle elements and actually apply visualization layouts to your data. This is a Hive plot using D3.js. Of course, this is just the beginning of information visualization tools. At some point, you actually have a need for something deeper and richer, or just something that's more specific to the type of tool that the type of goal that you have. Here's an example of something we did at Caltech where we needed to publish data resulting from simulations. What we created was a set of interactive visualization results that would actually remain static on an image until you put your mouse over it. The moment you put your mouse over it, you would get a full interactive tool that lets you change variables, draw things in 2D, 3D, change the different mappings of the variables, and even let you interact with different plots on the same page. If you highlighted points in one area, they would get highlighted in the other plots as well, same as we showed in Modrian a little while ago. So clearly the landscapes for tool out there is quite vast. And there's lots of different tools that are out there that are available that let you do this quick visualization, this quick inspection of whatever results you have coming out of your scientific computations.